Chapter 19D, Reactions of Aldehydes and Ketones, Oxidation, and Conjugate Nucleophilic Addition Reactions. In Chapter 17, we learned that an alcohol can be oxidized to an aldehyde by a mild oxidizing reagent, such as des-Martin periodinane. If a strong oxidizing reagent is used, such as chromium oxide, potassium permanganate, sodium chromate, then the aldehyde will be oxidized further to carboxylic acid. On the other hand, ketones are usually inert to the oxidation reactions. So go over these materials in Chapter 17 about oxidation reactions. In the following, we are going to introduce a new type of reaction called conjugate nucleophilic addition to alpha-beta unsaturated aldehydes and ketones. In ketones aldehydes, the carbon adjacent to the carbonyl carbon is called alpha carbon, and the next one is beta. When alpha-beta has a double bond, and this is called alpha-beta unsaturated aldehydes and ketones. As we know, the CO double bond is polar. Oxygen has a negative charge, carbon has a positive charge, and which can be shown by drawing this second resonance structure. For alpha-beta unsaturated ketones aldehydes, we can draw a third resonance structure to show that beta carbon is also positive charged. So for alpha-beta unsaturated aldehydes ketones, both carbonyl carbon and beta carbon are positive charged. So if we have a nucleophile, this nucleophile can attack either carbonyl carbon or the beta carbon. So far, all the nucleophilic reactions are concerning about this carbonyl carbon attack. So today, in this section, we are going to see some reactions that nucleophilic addition at the beta carbon, which is called conjugated nucleophilic addition. The result is that the nucleophile add to the beta carbon, and pi bond break, and the alpha carbon adds to a hydrogen. When a nucleophile attacks carbonyl carbon, the pi bond break leads to an ethoxide intermediate, which is protonated to give you the final product. This reaction only involves carbonyl carbon and oxygen, and it's called 1,2 addition. Examples include cyanide attack, hydride reduction reaction, Grignard reactions. When the nucleophile attacks beta carbon, the pi bond between carbon 1, carbon 2 break. 2 electrons go to carbon 2, carbon 3 forms a new double bond. At the same time, the pi bond between carbon oxygen move to oxygen forms a negative charge. This structure resonance. One of the lone pair electrons between oxygen come back to reform the CO double bond. At the same time, the pi electrons between carbon-carbon move to the alpha carbon, forms a carbanion. These two resonance structure represents a enolate ion. This enolate ion can be easily protonated by an acid, so that the carbon alpha carbon adds an hydrogen, and that gives you the final results. So if we compare the reactants and the results, you can see the CO double bond is untouched. The only change is the pi bond break, hydrogen adds to alpha carbon, nucleophile adds to the beta carbon. All right. However, the mechanism involves all 4 atoms, carbon 1, carbon 2, carbon 3, atom, oxygen 4. So all of them, and therefore the reaction is called 1,4 addition. But the net results only involves the CC double bond. Nucleophile adds to the beta carbon, hydrogen adds to the alpha carbon. Here shows an example. 2-cyclohexanone is a alpha-beta unsaturated ketone. When this ketone is treated with primary amine, and suppose the reaction is 1,2 addition, amine will attack carbonyl carbon, okay, gives you this epoxide intermediate, followed by protonation, deprotonation, CN double bond reform, many more steps, and the result should be a CN double bond and imine, as we already learned in the last section. However, experiments show this is not the case. Imine is not formed. Instead, it's the beta carbon as a amine. So the double bond, CC double bond, is replaced by amine and a hydrogen. Apparently, this reaction undergo 1,4 addition. So the amine adds to the beta carbon, pi bond move to here, and this pi bond move to oxygen, gives you this intermediate. And this intermediate resonance, the lone pair electron of oxygen move here, reform C and CO double bond, and this pi bond moves to the alpha carbon, forms a lone pair electron with a negative charge, which can be protonated, give you this product. Okay, so the net effect as you compare reactants and the product is that the CO doesn't change. It's the carbon-carbon bond break, adds alpha as a hydrogen, beta as amine, and that's 1,4 addition. Some nucleophiles prefer 1,2 addition, others prefer 1,4 addition. For example, when cyclohexanone is treated with a Gilman reagent, the Gilman reagent is lithium diorganol copper reagent. In this case, it's dimethyl. So methyl, dimethyl connect to copper with lithium as counter ion. Both methyl are carbanion. So the carbanion will attack the beta carbon of this unsaturated ketone, and then the pi bond move here to the oxygen. So the product is this intermediate, where the beta carbon adds a methyl group. Pi bond move to here, oxygen becomes negative charge, and the resonance structure goes to here. That give you double bond here and methyl here. You have a lone pair electron, a negative charge on the alpha carbon. Then this protonate, and that give you this product. Okay, so Gilman reagent undergo 1,4 addition. So it's methyl adds to the beta carbon, hydrogen adds to the alpha carbon. CO double bond is untouched in the end. Okay, but in the reaction it does involve participate in the reaction, so that's why it's called 1,4 addition. On the other hand, if this ketone is treated with Grignard reagent, here the metal is also a carbanion. Now this carbanion will add to this attack this carbonyl carbon, forms a epoxide protonation, and that gives you the 1,2 addition product. Here briefly shows the reaction mechanism involving the Gilman reagent. So the dialkyl copper initially adds together to the beta carbon. The pi bond move to oxygen, give you this intermediate, and then this rearrange. So one alkyl group with copper come out, and the other one adds to the carbon. Okay, and then this structure resonance. So come back, CO double bond, and the pi bond move to this alpha carbon, forms negative charge, which is protonated. That gives you the final product. In summary, in alpha-beta unsaturated ketones aldehydes, Both carbonyl carbon and beta carbon have a positive charge. They are subject to nucleophilic attack. With Grignard reagent, the carbanion attack the carbonyl carbon, give you 1,2 addition. The product is an alcohol. The double bond does not change. Amine, however, undergo 1,4 addition. Nitrogen attack beta carbon. The alpha carbon adds a hydrogen. CO double bond does not change. Remember, the mechanism involves all these 4 atoms, and that's why it's called 1,4 addition. Gilman reagent also undergo 1,4 addition. Hydrogen and carbanion adds to the double bond. CO double bond doesn't change. Water hydration also undergo 1,4 addition. In proton NMR, aldehyde proton signals are near 10 ppm. At NEL, for example, this hydrogen absorption at around 9.8 with a quartet pattern, and this is due to the coupling with these 3 hydrogens of the neighboring methyl group. In carbon-13 NMR, the carbonyl carbon signal is between 190 to 215. In ethanol, for example, this carbon absorption at 200. Benzoaldehyde, the carbonyl carbon is 192. Let's go over the reactions involving ketones aldehydes we learned in this chapter. The major reactions are nucleophilic addition reactions. The nucleophiles may be strong negative charged nucleophiles, and the mechanism has 2 steps: nucleophilic addition followed by protonation. These nucleophiles include the sodium boron hydride. The product is an alcohol. Grignard reagent. The product is alcohol with an alkyl group added to the carbon. Cyanide. The product is cyanohydrin. A new reaction is called Wittig reaction, and the reactant is an ylide. The product is to convert the CO double bond into CC double bond. The nucleophiles may be neutral, weak nucleophiles, and these include alcohol, water, amines. These reactions require acid as a catalyst. The first step always protonate the CO double bond, and these undergo many more steps: protonation, nucleophilic addition, deprotonation, and sometimes second attack. With alcohol, it first forms a hemiacetal. Eventually, it will give you acetal, where the carbonyl carbon is connected to a alkoxide. Acetal is one way to protect ketone aldehydes. For water, the hydration reaction gives you 1,1-diol. Primary amine give you imine. Secondary amine give you enamine. A special primary amine is hydrazine. When treated with hydrazine and a strong base, the product is to convert the CO double bond into 2CH bond, and that's an alkane. Ketones does not undergo oxidation, but aldehydes can be oxidized to a carboxylic acid if the oxidizing reagent is a strong oxidizing reagent, including chromium oxide, all right, or sodium chromate, or potassium permanganate. These are the homework problems.